Hey everyone! If you're an infrastructure admin gearing up to absolutely crush the Nutanix NCP-MCI 7.5 certification, you are in the exact right place. Today, we're diving into a highly focused, in-depth explainer titled NCP-MCI 7.5, 4.7, Mixing Nodes and External Storage. And just so we're totally aligned, we'll be looking at this strictly through the lens of AOS 7.5 and AHV 11.0. Now listen, this isn't just about cramming flashcards. It's about fundamentally understanding the underlying architecture so that you can walk into that exam room with absolute confidence.
All right, let's take a quick look at our game plan for conquering Objective 4.7. We're going to cover 1. Why mixing rules actually matter, 2. The mechanics of mixing drives and nodes, 3. Host minimums, 4. Bridging the gap with external storage via volumes, 5. Those tricky exam traps, and 6. A cheat sheet of the core facts you absolutely need to memorize. Let's get right into it.
Kicking things off with Section 1, Why Mixing Rules Matter, the Engineering Logic. So Nutanix mixing rules, they aren't just arbitrary roadblocks thrown in to make your certification harder. To really understand them, you've got to internalize this direct quote right out of the documentation. A cluster that contains different node types operates at the capabilities of the lowest media tier. When you're designing or expanding an environment, any mixing directly impacts the entire cluster, because the system is always going to default to the lowest common denominator. Think of it like a convoy of trucks. The whole group can only move as fast as the slowest vehicle. If you drop a slower, older node into a blazing fast, modern environment, you have literally just placed a speed limit on your entire architecture. Keep this rule in the back of your mind. It really is the foundation for everything we're about to talk about.
Moving right along to Section 2, Mixing Drives and Nodes, Navigating Tiers.
Before we get into the heavy rules, let's make sure our foundational vocabulary is rock solid. First up, WSS, which stands for Working Set Size. Basically, this is the chunk of data your application is reading or writing constantly. Your SSD tier absolutely must be large enough to handle this. Otherwise, you're looking at some serious performance degradation. Next, we've got CO, which are compute-only nodes, then SO for storage-only nodes, and finally HCI, which is your standard hyperconverged infrastructure node doing both compute and storage. You're going to see these acronyms constantly on the exam, so definitely lock them in now.
Okay, so when you're combining different drive capacities inside a single storage tier on a node, you're going to run into a very strict SKU rule. Look at the math we have mapped out here. If you've got 16 terabyte and 18 terabyte HDDs sitting together, that is a fully supported mix. Why? Because the difference, the SKU, between them is less than 20%. But try to mix 14 terabyte and 18 terabyte HDDs? No way. That is totally unsupported because the SKU crosses that strict 20% boundary. You literally cannot just throw random drives into a node and expect the cluster to be okay with it.
So let's talk about the why. Why is Nutanix so rigid about that 20% boundary? Well, it's because larger drives are inherently targeted for initial writes. If your drive sizes are wildly mismatched, the system is going to constantly, and I mean constantly, try to balance out that data across those uneven drives on the back end. What happens is you create this endless, exhausting balancing loop for the controller VM. And for your end users, that translates directly into some really severe and unpredictable performance fluctuations. It's just bad news all around. Now let's zoom out and talk about mixing at the node level. This matrix is a classic trap for the NCP-MCI exam, so pay close attention. Say you have a hybrid cluster, meaning your nodes have both flash and spinning disks. Can you add all flash HCI nodes into that cluster? Yes, you absolutely can. It's fully supported. You're essentially just upgrading the cluster's overall capabilities. But let's flip that scenario. Say you have a pristine, lightning-fast all-flash cluster. Can you add hybrid HCI nodes to it? Absolutely not. That is not supported. It's a one-way street, folks. You can never downgrade an all-flash cluster by introducing slower hybrid nodes.
Let's keep this rolling with Section 3, Hypervisors and Host Minimums, Building Mixed Clusters.
I highly recommend grabbing a mental screenshot of these host minimums. Whenever you are deploying storage-only, or SO nodes, the absolute baseline required to form that foundation is 3 nodes. You literally cannot start with fewer than 3 AHV storage-only nodes. And when you go to pair them with compute-only or standard HCI nodes, and honestly, it doesn't even matter if you're running AHV or ESXi hypervisors for the compute, you must have a minimum of 2 of those compute-providing nodes. Take a second to really absorb those numbers. 3 storage-only nodes, 2 compute or HCI nodes. That is your absolute minimum, non-negotiable baseline for building out mixed environments.
All right, Section 4, External Storage via Volumes, Bridging the Gap. This is where the architecture gets really interesting, showing off the true power of Nutanix volumes. If you trace the path on this setup, you'll see we have our standard hyperconverged infrastructure acting as the base. But by leveraging Nutanix volumes, the cluster actually acts as a target, using the iSCSI protocol to present scale-out block storage straight up to physical, bare metal servers. This is huge. It means your non-x86 servers, or those massive physical SQL and Oracle databases, can directly consume Nutanix storage just like it was a traditional SAN, but you get to keep all the sweet benefits of hyperconverged redundancy. But, and this is a massive warning you need to heed, there is a hard rule in the documentation you cannot ignore. Do not use Nutanix volumes to create an iSCSI data store for Hyper-V or ESXi hosts. Nutanix volumes is specifically designed for guest VMs and bare metal physical servers. It is absolutely not meant to provide underlying data stores back to other hypervisors. Trying to do that is entirely unsupported. It's a fantastic way to corrupt your architecture, and for sure, it's a great way to lose points on the exam if you fall for it. Which brings us right into Section 5, Exam Traps and Edge Cases, the Minefield. Let's rapid fire through some major gotchas that love to show up on the test. First up, the NVMe storage tier, or NST. This is your high-capacity, low-endurance SSD tier, and it does not support standard HCI workloads or hybrid drive configurations. It's a highly specialized use case. Second, if you're running an Optane performance tier, listen to this. It will automatically disable itself if even a single node in that cluster lacks Optane drives. It is an all-or-nothing deal. All nodes must have NVMe and Optane. And third, AOS actually has a really smart built-in guardrail. It will actively step in and block you from adding standard HDDs to an existing NVMe and NST cluster.
Here's another one to file away, the golden 2-to-1 ratio. If you're building a hybrid node, your standard ratio of hard disk drives to solid-state drives needs to be 2-to-1. The physics behind this is pretty straightforward. You need enough raw bandwidth on those slower spinning disks to actually catch and absorb information lifecycle management, or ILM, down migrations. As data gets cold, it cascades out of your faster flash tier down to the HDDs. If you can't maintain that 2-to-1 ratio to handle the flow, Nutanix basically recommends just going all flash. Now, because there is always an exception in IT, yes, exceptions exist for this rule, but they are strictly limited to very specific hardware configs from Dell, Lenovo, and Fujitsu.
We are almost at the finish line. Section 6, Core Facts to Memorize, the cheat sheet. Let's lock these in.
20. This is the absolute maximum percentage skew allowed between drive capacities within a single storage tier on a node. If you go beyond 20%, you are asking for endless back-end rebalancing.
3, this is the absolute bare minimum number of storage-only nodes required when you're building out a mixed node architecture. You literally cannot start with anything less than 3 SO nodes. This is the minimum number of compute-only or standard HCI nodes you need when you're pairing them up with those storage-only nodes. So again, 3 for storage, 2 for compute.
All right, so you've now got the strict limits of mixing nodes, dealing with drive skews, and safely presenting external storage via volumes totally locked down. But I want to leave you with something to chew on. How will these rigid structural constraints ultimately dictate your disaster recovery and replication strategies? When you start architecting metro availability across different physical sites, these exact minimums and mixing rules suddenly become even more critical to your success. Definitely keep that in mind as you transition into your next study topic. Thanks so much for hanging out and learning with me today, and good luck crushing that exam.